Hello. I would like to give you a short background on the bivariate statistics that we will be using to analyze the survey that you created last week. We'll be talking about chi-squares and t-tests of independent samples. Now, our goal is to test bivariate relationships, and that means we're testing the relationship between two variables. Now, all of these are inferential procedures rather than statistical procedures. That is, they test relationships or claims or hypotheses in the data. Each procedure then represents the test of a hypothesis, actually two hypotheses, both the null hypothesis and the scientific hypothesis. Even if one doesn't state them explicitly, each of these bivariate tests represent an implicit test of a hypothesis. So let's do a quick review on hypothesis testing to begin with. First of all hypotheses testing uses, actually the hypothesis is stated in terms of a population. And the goal is to make a claim about a population using the variables and the data in a sample. Again, because today we're dealing with bivariate statistics, the hypotheses that we will write have to do with the relationship between two variables. In a survey, the goal is to use a sample to represent a population of interest, so that's consistent with hypothesis testing. There are 4 steps in hypothesis testing. I just want to refresh these with you, and you'll see how we actually will combine them in class. First, we state a hypothesis. The null hypothesis, or H0, is typically a hypothesis about no change, that there's no change, no difference, or no relationship between two variables. The alternative, or scientific hypothesis, typically states a change, a difference, or a relationship between two variables. So step 1 of hypothesis testing is simply to write these out. Here's an example. Let's say we're interested to know whether female students are more likely to join campus organizations than male students. Well, in this case, we can think about the sex of the student as the independent variable, the potential cause, and the membership in a campus organization, that is being a member or not a member, as the dependent variable, or the outcome. You see below I've listed the null hypothesis and the alternative, also known as the scientific hypothesis. The null hypothesis, the percentage of students who are members, is the same for male and female students. The null hypothesis, or the scientific hypothesis, is that they are different. Step 2 of hypothesis testing is to set a criteria, also known as alpha. We talk about level of significance, and it's from that alpha that you actually find a critical region and reject or retain the null hypothesis. We won't spend too much time with this. Just you should recall that the typical level of alpha is 0.05. Step 3 is to collect data and compute sample statistics. Technically, we should be collecting data only after we've stated our hypotheses, but this isn't always the case. The sample statistic we're talking about could be a chi-square, like we're going to use today, or a t, and it's compared to a critical region that's specified in step 2. This should be bringing back some memories of statistics. Step 4 is making a decision. If the sample mean is in the critical region, and we can assume that p is less than 0.05, for example, we reject the null hypothesis. More about this in a moment. Parametric statistics, let's see if we have a list here. Parametric tests, we run parametric tests to test hypotheses when we are dealing with a variable that's normally distributed, has a certain homogeneity of variance, and has a numerical score for each individual. So we use parametric tests for ratio variables, ratio data, and interval data, and in some special cases, ordinal data. So if something's measured on a ratio or interval or in some situations, an ordinal scale, we can use a parametric test. Non-parametric tests are needed when the research situation doesn't fit those criteria. So, for example, when we have data that are nominal, or at best ordinal. So speaking of which, what's our principal non-parametric test we're going to be using? Well, it's the chi-square, which is also denoted with a lowercase Greek x, chi-square test for independence. This test for the existence of a relationship between two variables. The variables are either nominal or ordinal. The null hypothesis for tests of independence is typically that two variables are independent of one another. There's not a relationship between the two variables. Here is the example of a chi-square. Let's say we're looking at how often one applies makeup before one goes to school. And we had a scale or we had a variable which is at best ordinal. I never apply makeup. I apply it every day. I apply it 1 to 2 times a week. I apply it to 3 or 4 times a week. You can see most folks in this sample, 63% never use makeup before going to school, 19% say every day, and another 18% or so say a few times a week. In this survey, we also had males and females, split pretty evenly, 50 and 50. Now let's say we wanted to use a chi-square to test the relationship between frequency of makeup and sex of the respondent. What would be your prediction in terms of frequency of makeup and sex of the respondent? Let's see what the chi-square tells us. Now here's a chi-square. Oops. Here's a chi-square. Let me show you some points. First of all, over here you see the total frequencies for frequency of makeup. About 62% of those in the complete sample never wear makeup, and then you see the other percentages here. These numbers in the total don't necessarily add exactly up to these numbers because we did lose some cases because of missing data. You can see some missing data there and there. These two columns represent two levels of the variable sex, sex having male and female. And this is the breakout of percentages of those frequencies of wearing makeup by male and female. You notice that among males, 94% of males say they never wear makeup to school, and 3% say every day, and 3% say 1 to 2 times a week. Notice that 31.4% of females say they never wear makeup to school, and actually about a third say every day, just under a quarter say 1 or 2 times a week, and another 10% say 3 to 4 times a week. Here's the actual output of the chi-square test. We just showed you the crosstab, or the frequencies that are being tested. Here you see the output of the test. You notice that, let's look at this one row, the other rows aren't relevant to us right now. This is the actual chi-square statistic, a Pearson chi-square. So the value of this Pearson chi-square is 29 with 3 degrees of freedom. This is the significance level, or two-sided, assuming a two-sided chi-square, which we are. And we would conclude here that P is clearly significant. It is less than 0.05. In fact, it's less. It looks like it's 0.0001 or so, which is clearly less than 0.05, which was our critical value and clearly significant. Therefore, there's a difference in the distribution of frequencies for males and females, indicating there is a difference between males and females in terms of frequency of makeup, and the direction of the difference is that females are more likely to wear it. Now let's think about parametric tests. And so for data that is interval or ratio, we use a t-test, or we'll use a t-test of independent samples. As I said, test difference in ratio or interval data. It's based on two levels of another variable or another independent variable. It asks the question, do the means of one variable differ between two levels of another variable? The null hypothesis is stated as the difference in two means is equal to 0. Now if you think about it, if the mean for one population and the mean for the other population is the same, you subtract one from the other, there's 0. The alternative hypothesis is that there's a difference in the means, or subtract one from the other, it's not going to equal 0. I already said that. I will skip over the formulas, which are quite daunting for the t-test, and go directly to an illustration. Let's say we have two different treatments, and the mean for one treatment is 8. The mean for the other treatment for people in the other treatment is 13. You can see them laid out here. This has a nice distribution around 8. This has a nice distribution around 13. These clearly look like they're different treatments. Look like they're coming from, there's something different about the people receiving this treatment and this treatment. On the other hand, you could have a situation where your means are still 8 and 13, but the variation is far greater. So you see treatment 1 varies all the way from 0 to 18. You see that treatment 2 varies all the way from 3 to 21. Because of this, this will probably not be a statistically significant difference, whereas this one, because of the small variation in each, probably will be statistically significant. So turning to surveys, here's the example of a t-test. The last year we asked students, how many minutes does it take you to do your hair? And you can see the frequency here. It ranges from 0. For some students it took them no time at all to do their hair, at least 22% of them, up to some students who said 120 hours, 120 minutes or 2 hours, hour and a half, 1 hour, and on down. So if you look at the summary statistic, the average amount of time, if you look across everyone, was about 10 minutes to do your hair. But we might ask the question whether the amount of time it takes to do your hair varies by sex of the student. So again, we had sex of the student we looked at before, and if we look at the means broken out by sex of the student, we see it takes males an average of 1.26 minutes to do their hair, about a minute and a half, and it takes women an average of about 18 minutes to do their hair. The t-test tests these two differences. If there's no difference between these two means, if the means are pretty similar, that means that the amount of time it takes to do your hair doesn't vary by sex. So the null hypothesis is going to be there's no difference in these two. The alternative hypothesis is that there is a statistically significant difference between these two. Here is the actual test, and this is the kind of printout you'll see when we do our analysis. Let's see. This is actually the t statistic. Here is the t statistic. Here's the degrees of freedom. And here is the probability, or the p-value. If you notice that the p-value here is less than 0.05. In fact, it's 0.001. That tells us that we should, again, reject the null hypothesis that there is no difference between these two we reject the null hypothesis that there's no difference between males and females. This is statistically significant, indicating that this is a statistically significant difference between them. Now, I'm not going to ask you to do all of this work. I wanted to refresh your memory about these two approaches, the chi-square and the t-test. Here is your homework, which should take about just a few minutes to do, and no statistics. What I'd like you to do for class is to, there's actually a forum online in Angel, and what I would like you to do, and this is summarized in that form as well, is to list variables from the survey that you would like to analyze for your lab report. There may be one variable you're interested in, there may be two, but you need to list them specifically. Second thing you need to do is to list the variable that you'd like to use as the independent variable. So these are the dependent variables. You'd like to understand whether these vary by one of the independent variables that we can look at. These are, well, we could look at sex, we could look at the major, or you might find another category, two-category variable that we could use. So I'm interested to hear. For each of the variables listed in 1 and 2, identify the scale of measurement, nominal, ordinal, interval, or ratio. Then identify which bivariate analysis you would use, a chi-square or a t-test. And finally, write out the null hypothesis and the alternative hypothesis for each analysis you specify. Do not do any statistics. You don't have the data. Don't worry about formulas. I just want you to identify the variables and the null and alternative hypotheses. As always, let me know if you have any questions.